So we're finished up section 2.2 today, and we can get started in section 2.3 a bit. So let's see. We looked at one-sided limits to help us decide geometrically. We have a picture looking at us, or by crunching numbers, if a function had a limit. If the limit as x goes to a from the f of f, x goes to a from the left of f is L, and limit x goes to a from the right is also L, then that's what we say the limit is. So we can do that when we plot a bunch of points. If these two go to different places, then we say the limit does not exist. One of these on that sheet or not. I'll do one right now. I'll do one right now. For example, you can find the limit as x goes to 2. We'll put x minus 2 on the bottom. I'm going to put an x minus 2 on the top, but I'm going to put the x minus 2 on the top in absolute value. So I want to find that from the right, from the left, and without regard to direction. Is that something that you know the graph of? The absolute value of x minus 2 over x minus 2? Then we'll just do this by plotting a few points, because this won't be hard to plot points. We don't need a calculator for that. For this one, we're going to pick numbers that are slightly larger than 2, like 2.1, 2.01, and 2.001. So in both cases, I have to take 2.1 and subtract 2. So I'm going to get 1/10, and it's going to be a positive 1/10. So on the numerator, I get the absolute value of 1/10 divided by 1/10. Looks like 1 to me. Now I'm going to put in 2.01. When I subtract 2, I get 0.01. It's positive, so I get 0.01 over 0.01. Again, I'm getting 1. Does it matter how close I get to 2? Put 2.001 in there. Since it's bigger than 2, I get 0.001 here. The absolute value of 0.001 here. So I just get 1 again. I'm going to go out on the limb and say that the limit as x goes to 2 from the right is 1. You can agree with me? Okay, what will be different if I pick numbers that are smaller than 2? Anything? So smaller than 2. So let's go with a 1.9. Okay, let's go with 1.1. Yeah, 1.9 is good. 1.99. 1.999. Those are all approaching 2. If I put that in down on the bottom, 1.9 minus 2 is a negative 1/10. On top, I have a negative 1/10 in absolute value bars. So my numerator is going to turn out to be a positive 1/10, but my denominator is a negative 1/10. So here I should get a -1, right? If I put that one in there, 1.99 minus 2 is a -0.01. So when I take the absolute value of that, I get a positive 0.01. But on the bottom, I have a -0.01. So I'm going to get a -1 there as well. Same thing here. So what we have is this situation. Here's x is equal to 2. For every number to the right of 2, this thing is at a +1. For every number to the left of 2, this thing's down here at a -1. And there's not a y value at all when x is equal to 2. And now I use this. The two one-sided limits are not equal. There's a big old jump in the graph right there. So we say that this limit does not exist. Okay? So sometimes we do have to plot some points. Sometimes we can use algebra. If we get 0 over 0, okay, so our plan in calculating limits, if we can plug the number in, and get a number back out, and that's our limit. Right? We said that are nice functions, things that don't have any breaks in them. So the limit should be the same as the y value. If we get 0 over 0, then we do more. So what we've seen is sometimes if we had polynomials on top and the bottom, we tried to factor and cancel. If we had some stuff that maybe wants us to square or multiply stuff out, we did that. We did an example where we had to rationalize either the denominator or the numerator to get something to cancel. And then we had our two special trig limits. Our two special trig limits were this one we found by plugging and chugging. As x goes to 0, the sine of x divided by x. Does anybody remember that one? That was 1. And then the other one was as x goes to 0, of 1 minus the cosine of x over x. What'd that one do? Yeah, our other favorite number. The other trig limits come from the fact that our trig functions are nice continuous functions. So for instance, if I took, I'm going to erase that junk in the middle. Maybe. Anything up here look like an eraser? It happens. You just wake up and it happens to you. No. Just that. Gosh, darn it. Oh. I bet it took you a while to get brave enough to say that, didn't it? You know, some mornings when I run out of milk and I got my bowl of cereal poured already, I don't want to put it back in the box. A little vodka on it. So other trig limits. Suppose I had the trig functions by themselves, just the sine of x as x goes to 0, the cosine of x, tangent of x. What do you think? What's the limit as x goes to 0? The sine of x. It's a sine of 0. Close, close. Sine of 0 is 0. Sine of 0 is 0. And since this is a nice function at 0, we can plug the number in, get a number back out, and that's our limit. What about the cosine? As x goes to 0, what's the cosine of 0? That one's 1. And the tangent is the sine over the cosine, so 0 divided by 1 is going to be 0. All right. Now, 1 over the sine is the cosecant, so as x goes to 0, that's not going to be defined. 1 over the cosine is the secant. As x goes to 0, the limit of the secant will be 1 over 1. But this 1 over tangent or the cotangent will not be defined there. Okay, so let's get back to our sheet. Does anybody know where we left off on the class examples?
What, 13?
13?
Or we did it.
You did it? All right, so we're going to do some of this stuff with trig. Take the limit as x goes to 1 of the sine of x minus 1 divided by x minus 1. So we try that bit where we plug the number in. If we get a number back out, then that's our limit. What happens when we plug that number in? You get 0 over 0, right? Because the sine of 0 was 0. We saw over here that when we had a sine of 0 over 0, that should be 1. So that's our intuition, that that's going to go to be 1. But we're going to do it formally. We're going to make that look just like this. So the first thing I'm going to do is I'm going to say let x minus 1 equal some other letter. I'll go with the Greek letter theta. So as x goes to 1, notice that theta goes to 0. As x goes to 1 right here, theta goes to 0. So I can rewrite this now in terms of the variable theta as the sine of theta over theta. And now it is my special limit. And since I can say that that limit using my number 1 over there is 1, then I'm done. Shift it over a little bit. Okay. Fifteen says, all right, it can be very similar. The limit as x goes to 0 of the sine of 3x divided by x. We try this business about plugging the x in. So on top, I get the sine of 0 is 0. On the bottom, I get 0. So I get 0 over 0. I want to make this come into play by mimicking what I did there. So I'm going to do a change of variable. I'm going to replace the 3x with the variable theta. So I want this to match that. So I'm going to put a 3 here. But if I put it down there, I have to take it back out. So I'm gonna take it back out right here. So I'm multiplying by 1. Now I'm gonna do that change of variable thing. I'm gonna take the stuff inside the parentheses and say that it's equal to theta. And then as x goes to 0, so does theta. So everywhere I have 3x, I'm going to replace it with theta. This 3 is just a constant. A constant times a limit is just that constant times the limit. So I can pull that blue 3 in front out. I'll make this a theta. And that a theta. Do this limit right here, using my special limit. That's not an x, that's a theta. That limit in there, we all agree, is 1. So I get 3 times 1, or 3. And if you like those steps, we can just make this a general rule. Let's make a most general rule or a more general rule. Suppose I want to take the limit as x goes to 0 of the sine of some number times x. Let's just use a k. And then another number times x. I'll essentially do the same thing. I'll replace k times x with the letter theta. I'll put a k down there with the x and take it back out by putting it on top. I'll take this n, it's just a constant, and pull it out front as a 1 over n. So here are the same steps. I put the k where I need it. I take it back out. I do the change of variable like I just did over here. Take this k out front, make that a k divided by n. Do the change of variable. Get that this limit is equal to 1. And then 1 times k over n is k over n. So if you want to understand those steps, then you can just use that as a general rule. So if I take, for instance, the limit as x goes to 0 of the sine of pi x over 8x, what do you think that limit's going to be? Pi over 8, using our special limit. Okay, but that's only if x goes to 0. What if I have the limit as x goes to 1? Well, if x goes to 1, I get the sine of pi over 8. So you got to remember what the sine of pi is. Anybody remember the sine of pi? It is 0. Okay, so this only applies to the 0 over 0 form. You plug the number in and get the number back out, then that's your limit. Okay, and so that was 15. Let's look at 16. 16's got a secant function in it. The limit is x goes to 0. Secant of x minus 1 divided by x times the secant of x. I just erased it. Who remembers what the secant of 0 is? Whatever the cosine of 0. 1. Secant of 0 is 1. Since the secant of 0 is 1, in the numerator I have 1 minus 1. In the denominator I have 0 times 1. So it has my 0 over 0 form. And it says do more. I can't just cancel secants there because the secant of x minus 1 is one term. I can't cancel anything through a sum or a difference. I can only cancel through a product. So don't try doing silly stuff like that. So the only other thing I have left to do is get the secants out of there and write them in terms of cosines and hope one of my two special trig limits show up. So let's replace every secant with 1 over cosine of x. What do you want to do next? Anything hit you that you might want to try? We'll clean that up a little bit. Gotta know what your algebraic thoughts are. All kinds of ways I can go next. Let's suggest something to me. I'm not fond of having a couple of fractions in my fraction. Are you fond of that? There's got to be a way to simplify that. Yes, ma'am.
Could you do x over cosine x, the bottom one, and then flip it?
And then flip and multiply. Let's do that. That's x over cosine of x. And so to divide one term by a fraction, you flip this one over and multiply. So let's distribute that through the parentheses. So when I take that times this, the cosines will cancel, leaving me with 1 over x. And then when I take that times that, I just have cosine of x over x. But there's no reason to write those as two separate fractions because they already have a common denominator. Let's go ahead and put them together as a single fraction. And when we do that, we get our other special limit. Right, see how I did that? Just the same denominator, right, as a single fraction. 1 minus the cosine of x over x is 0 as x goes to 0, right? So there's our limit. All right, number 17 has no trig functions. Maybe we can look at some other algebra. I put 17 next to kind of remind you of this. We've got the limit as x goes to 2. I got 2 over x minus 1 divided by x minus 2. So we make a quick check at what happens to the expression when x is equal to 2. And when x is 2, I have 0 on top, 0 on the bottom. So I tell myself I've checked that. Do more. This time my fraction's on the top, so I'm not going to do the flip and multiply step just yet. I'm going to put these two fractions together by getting a common denominator. I'm going to think of this one as being x over x. And then once I have a common denominator, I can put them together as a single fraction. So I'll have a 2 minus x over x. Then I have that divided by x minus 2. Now I'd like to do the step where I flip and multiply. So think of this thing as x minus 2 over 1. Flip it over and multiply it with the guy on top. These will cancel, but how? How are x minus 2 and 2 minus x going to be similar? I'm going to do that. You can't just pick my favorite term. That's one term. Right? So I'm dividing. And x is not going to 2. Oh, yeah, it is. But still 0 over 0. So I need to cancel. So that was my question. How do I cancel there? Take out a negative sign right there. If I factor out a -1, this becomes a -2 plus x. Or -1 times x minus 2. So the moral of the story is that x minus 2 and 2 minus x will cancel and leave behind a factor of -1. And so now I'm ready to take the limit as x goes to 2. I have -1 left on top and an x on the bottom. So now I can try putting the 2 in for the x and get a -1/2. So add this kind of idea to your list of things to try. Do the factor, cancel, rationalize, get a common denominator and add, and see what happens. Is anybody anywhere? All right, back to trig. I've got a tangent of 3x divided by the tangent of 2x, and x is going to 0. So x is going to 0. That leaves me a tangent of 0 over a tangent of 0. What's the tangent of 0? Tangent of 0, 0. So this has the form of 0 divided by 0. So we got to do more. And I don't have any special limits for tangents. My special limits involve sines and cosines. So let's jump and replace each of these with sines and cosines. Rewrite the tangent of 3x as the sine of 3x over the cosine of 3x. Do the same here, sine of 2x over the cosine of 2x. If you want to unstack your fraction, we can do the flip and multiply step now. Cosine of 0 is 1. So those cosines aren't giving me any trouble. It's the sines. So I'm going to take those two cosines and push them way out on the end and leave the sines by themselves. I'll write that as the sine of 3x. I'm going to write that times 1 over the sine of 2x times the cosine of 2x over the cosine of 3x. Just moving furniture. Now, if I had a 3x underneath here, or at least in x, I can use my special limit here. And if I had an x under here, I can use my special limit there. And that one's just going to have a limit of whatever happens when x goes to 0. So I'm going to put where I need it. I'm going to put an x here. But then I need to take it out here. So I'm multiplying by 1. I'm going to put an x here, but then I need to take it out here so that I'm multiplying by 1. You happy with that? Now I can take my limits. This limit is going to be how much? Will be 3, isn't it? That was the general version of the special limit. If there's a number in here and a number out there, we take the ratio of those two numbers. This limit is going to be 2. This x cancels with that x. I've got one on the top and one on the bottom. So that one is going to cancel with this one. So I have 3 is the limit here. 1 over 2 is the limit there. Cosine of 0 in each case is 1. So I can do my limit term by term. I get 3 times 1 over 2 times 1 over 1. And these x's cancel. So my limit's 3/2. Sneaky, huh? It's all algebra. Stick a number in, take it back out. We can multiply 1 by 1. That's legal in every state, including Arkansas. All right, let's try number 19 then. Taking the limit as x goes to 0. I've got the cosine of 2x minus the cosine of x all divided by x. So me try putting 0 in for the x's, and remember that cosine of 0 is 1. So I have 1 minus 1 over 0. We got 0 over 0. Go try something else. So we usually try to write things in terms of sines and cosines. Boom, it's already written in terms of sines and cosines. The problem, however, is that this is a trig function of twice x as a trig function of just x. And trig functions are not algebraic. I can't just pull this 2 out here. I sure wish I had some trig identities I could use. I do. We need to find a trig identity that writes the cosine of 2x in terms of the cosine of 1x. Got one anywhere? I looked at some trig identities the other day. They were kind of useful. One of them would be useful here. Sorry? The multiple angle, which is the double angle formula for the cosine. You have that written down somewhere? The double angle formula for cosine. Cosine squared of the single angle minus sine squared of the single angle. So we're going to use that right here. Cosine squared of x minus sine squared of x. So that is the identity that we're going to try. I still have 0 over 0, but at least now I have the same angle everywhere. There's still 0 over 0 though. I'm gonna try something. Gonna try to move it on from here. I don't know. Usually, I don't know how much messing around with trig expressions you do. But when I mess around with trig expressions, I like them all be not just in terms of the same angle, but in terms of the same trig function. So I'm going to get the sine squared out of there. I have an identity that lets me replace a sine squared with a cosine squared-ish.
1 minus cosine.
Sine squared is 1 minus cosine squared. So I'm going to get this out next. Another trig identity. Just keep playing with that. Keep playing with it. I'm going to take the parentheses away and distribute the minus sign. So when those parentheses are gone, I'm going to have a minus 1 plus a cosine squared. So I'm going to take the cosine squared that I get from here and add it to the cosine squared that I get there. Put that with that, and it's going to give me 2 of those. Then that becomes a minus 1, and I'm going to put the minus cosine in the middle. Two cosine squared of x minus the cosine of x minus 1 all over x. Still has the form of 0 over 0 because each cosine of 0 is 1. So this is 1 times 2 minus 1 minus 1. So that's still 0, that's still 0. But now it looks like something I can factor on the top. 2 cosine squared minus cosine minus 1 looks like a trinomial. What if I asked you to factor this? Say 2u squared minus u minus 1. Can you factor that? Again, I didn't even know what algebra you know. Can anybody in here factor that? Get the 2u squared, you need a 2u times u, right? First thought we'll have 2u times a u. Factors of 1, well, it's just 1 and 1. If I want that minus, these have to be opposite in sign. We need them opposite in sign so that my middle term is a minus u. So which of the two factors is going to get the minus sign? The second one, because that's the one that multiplies with the 2. For factors like that, the u is the cosine of x. So this looks like the limit as x goes to 0 of 2 cosine of x plus 1 times the cosine of x minus 1. Let's see if you can like this next step or not. Next step. You okay? Those equivalent expressions? I just took that second factor with the x, moved it over there, and kept that by itself. And I did that because this looks a lot like my special limit. My special limit had 1 minus cosine of x over x. I can make it look like 1 minus just by factoring out a negative 1. And then we can just take limits term by term. There's my special limit as x goes to 0. So in the blue box, what's the value of that limit? Limit is x goes to 0, 1 minus cosine of x over x. That's 0. Times that negative 1. Now x is going to 0 in here. Cosine of 0 is 1. 2 times 1 plus 1 gives me 3. But 3 times negative 1 times 0 is 0. So that's the handy dandy property of limits. You can take limits term by term in a product, term by term in a sum, top over bottom. You can go inside of square root signs, things like that. So I just rearrange it so that it looks like limits that I can take within the class. Or none of them are 0, 0 anymore, except for that last one, which was a special one. So that's all the examples I had for you. Does it make you think of anything you want to try? Anything from web work or?
So what about the questions where they're asking for limits, but they come in like a bunch of like equations and it says fx?
And you got a picture? You got a picture to look at?
I don't remember.
These slides when we're giving multiple equations.
Yeah. Like it's a piece like it's like multiple equations in like one. Like this one.
All right. I can do that one. I can do that one. Open the net. Leave it open. You're gonna call it to me because I can't read it.
Okay.
We've got a piecewise defined function. Problem number is this one?
For me, it's 1.
All right. This function has what, 3 pieces to it?
Yes.
All right. What does the top piece look like?
3x plus 4.
And for which x's does that hold?
X is greater than 5.
Okay, the middle piece?
X squared plus 2.
And for what x does that hold?
0 is less than x, but x is less than or equal to 5.
Okay, now the third piece?
X plus 6
I suppose that's for x.
is equal to, x is less than or equal to 0.
All right. How many of you would be able to graph that function? We've got a line, another line, and a parabola. But they change shapes according to where the description is. So let's just try drawing them. Picture will tell us almost everything. Over. There it is. All right. So to sketch a graph of a line, let's plot 2 points. Let's plot 5 and 6. So if x is 5, I get 15 plus 4 is 19. So let's put that right here. And let's put a hole because of the strict inequality. I really don't need another point because I've got a line of slope 3. So just make a steep line here. I don't have a scale drawn. Let's just make it look like that. Right? X is 5, y is 19. So the ordered pair 5, 19 with a hole because of the strict inequality. And if x is any other number bigger than not 5, it lies on a line of slope 3. Next, we have a parabola. And the vertex of this parabola occurs when x is 0 and y is 2. So let's put 0, 2 up here. If that's 19, 8, let's say 2 is about right here. And then it opens upward, but it stops that shape when x is 5. So let's put a 5 in for x. 5 squared plus 2 is 27. So the ordered pair 5, 27 is on this graph. If that's 9, let's put 5, 27 right here. And draw that parabola. So it makes a jump right here. The next piece is a line with slope of 1. When x is 0, y is 6. Let's say that that's here. And then a slope of 1, so it's going to come up this way. Oops, I missed it, so make a big dot. Okay. All right, now maybe the picture can tell us what the limits are. What are the limits that we need to find in the order?
Limit of f of x, x is 5 positive.
Okay. And then to the left,
X is 5 negative.
and then x is 5.
No, x is 0 positive, and then x is 0 negative.
And then that's it.
Yes.
But we'll add 2 more. We'll add the limit as x goes to 5 and the limit as x goes to 0. So 5 and 0 were the 2 places where the function made the jump. So you're going to describe the jump using limits. With the plus sign here, it says x is slightly bigger than 5, but coming toward x is 5. What are the y values heading toward?
What is that?
Bigger than 5 puts us on this piece.
Nice.
So as I move toward 5, the y values are moving toward 19. Now get a little bit smaller than 5 and get on the graph and start moving along that graph until x is real close to 5. And what y value are you close to?
27.
That's going to 27. And since those two numbers miss each other, we automatically say that the limit as x goes to 5 does not exist. Got to hook up in order for there to be a limit there. Okay, now I know this limit's not going to exist because they're not hooking up there either. If you're coming into the right of 0, to the right of 0, the piece of the graph looks like the parabola. So as x is moving closer and closer to 0, you're sliding down that parabola closer and closer to what y value? 2. Good. When you're to the left of 0, you're riding up that line. So what y value are we approaching as x gets near 0 from the right? I'm sorry, from the left. 6. And since those two, oops, I need an f of x here. Since those two missed again, this one does not exist. If I pick a number that's not one of the jumps, then we've got the case where you can just plug it in. Like for instance, what is the limit as x goes to 1? So I have to find out where I'm living. When x is going to 1, we're on the parabola. When x is going to 1, we're going to 3. What about if x goes to -1? X is -1, we're on this line. That's this one. -1 plus 6 is sending me to 5. That all make sense? So we're going to be able to describe where a function has these jumps by looking at one-sided limits. But we were lucky we had the picture. We didn't need the picture. If I'm going to 5 from the right, I look at where x is bigger than 5 here, and then I put the 5 in. I don't have to have a y value there, right? Because of the strict inequality. I just have to get real close to it. Okay. Picture helps, but the picture is not vital. I can still plug those numbers in into the right piece, just like we did with the 1 and the -1. What else? Yes, sir.
I think it's number 11, I'm not sure.
Number 11-ish.
Yeah.
Okay.
Its limit is x approaches 0. The fraction is sine of 4 theta times theta. Over theta squared.
I'm gonna change that x to a theta. That should be a theta there. And that's an awful small 0, so let me make that bigger. So we try putting 0 in for each theta. For the bottom's trouble, I've got 0 squared. Sine of each of these when theta is 0 are also 0. So I have 0 times 0 over 0. That's a do more situation. But the theta squared is kind of nice. I'm going to write the theta squared as theta over theta. It's not theta over theta, theta times theta. Like this. Agree with that product using on the line above? But now it looks like the general case of my special limit. Sine of kx over nx as x goes to 0 is k over n. So in each case, I have a 1 here. So this limit is 4 over 1. This limit is 9 over 1. So I get 4 over 1 times 9 over 1. Just grouping those as a special limit. So I get 36. Anybody got another? Okay, then I've got about 15 minutes to talk about section 2, 3. I can.
Okay. It's number 9. Okay, so the limit x approaches pi over 4. And then on the top section is 4 parentheses sine of x minus cosine of x. And then on the bottom is 3 cosine and then 2x.
All right, so let's try putting pi over 4 in for x. It's the sine and the cosine of pi over 4. Sine of pi over 4, cosine of pi over 4. What are each of those? Both of them are square root of 2 over 2. So this is going to be square root of 2 over 2 minus the square root of 2 over 2. I'm going to get 0 in the parentheses there, which gives me 0 on top. Take pi over 4 and multiply it by 2. 2 pi over 4 reduces to pi halves. What's the cosine of pi halves?
Yeah.
That's 0 as well. So we got 0 on top, we got 0 on the bottom. That says to do more. Last time we had our angles mixed up. We were able to use a double angle formula. It worked. It works once. Why don't I want to work again? Let's whip out that same double angle formula for the cosine of 2x. Let's replace the cosine of 2x with cosine squared of x minus sine squared of x. We're going to use our double angle formula. That help anybody? I'm looking for suggestions from here. Think about this. On the bottom, look like the difference of squares. Is the difference of squares factor? How does a squared minus b squared factor? What's that factor? Tell me. Don't be shy. That's right. Difference of squares, that's what we have on the bottom. Cosine squared minus sine squared should factor as cosine minus sine times cosine plus sine, both as functions of x. So I'm using that. Time to see what's gonna happen. That factor looks a lot like the one above it, just turned around. That means it has a common factor of -1 in there. So I'll put the negative with the 4. And turn that around. And next step, it'll cancel. Cancel here, write down what's left. I'm not gonna have 0 over 0 anymore because I just have a 4 on top, a -4. On the bottom, I have 3 times cosine of x plus the sine of x. So I can take the limit of that by plugging those numbers in. And remember, sine and cosine at 5/4 are square root of 2/2. So we have -4 divided by 3 times the square root of 2/2 plus the square root of 2/2. Square root of 2/2 plus square root of 2/2 gives you 2 square root of 2/2. The 2's cancel, and it leaves you with square root of 2. And that's our limit. We just had to find where the 0 over 0 was coming from. There was a common factor or a special trig limit. This one is a common factor.
Do you have to rationalize?
Nah. Good. Anything else, anybody? All right, section 2-3 then. Section 2-3. That away. That away. If something is continuous, then it's not broken. It just goes on and on and on without any breaks or interruptions. A function's continuous, it has no breaks or interruptions in it. Here's a function that is continuous for all values of x. Draw it without picking up the pencil. Right? There are no breaks, jumps, or holes. Breaks, jumps, and holes are examples of discontinuities. A function has a discontinuity if there are breaks, jumps, or holes in it. Most of the time a break shows up as an asymptote. So if this is the number line and this is x is equal to a, and there are no y values there, then your function might look something like this. There's a break of an asymptote at x is equal to a. A jump, well, we've seen a piecewise defined function that had jumps in it. There's x is equal to a. We had one that did something like that. And then something like that, made a jump at x is equal to a. And then a hole, well, that a lot of times appears with our 0 over 0 case, that there's a hole in it. Might have a y value somewhere else, but it goes along minding its own business, and then all of a sudden there's a hole in it. And then it picks up back where it was. Those are examples of discontinuities. We can find these using limits. A function is continuous if it has no breaks, jumps, or holes. I'm going to write up 3 functions up here. I want to change their names. There are 3 functions for you. And all 3 of them look very, very, very similar when you graph them. So I'll graph them. The easiest one to graph is the one in the middle. That's just the line y is equal to x plus 2. Here's the graph of g of x. When x is 0, y is 2. When x is negative 2, y is 0. There's the graph of g of x. Just a pretty little line. So notice that g is continuous for all x. The other 2 functions have an x minus 2 in the denominator. So I'm a little bit suspicious of what happens to those 2 functions when x is equal to 2. So we're going to call that a suspicious point. Everything else looks okay, right? Just dividing by 0 looks. Same thing here. I'm wondering what's happening at x is equal to 2. That's my suspicious point. Well, this tells me what's happening at x is 2. At x is 2, I have a point. But I got to know, does that point appear to fix this discontinuity at x is 2? Here, when x is 2, I get 0 over 0. So I know there's a hidden factor in there somewhere. Or factor the 4 minus x squared for me. When I'm factoring, I'm looking at a limit. I'm looking at the limit as x goes to 2. That's going to factor as the difference of squares. A squared minus b squared factors as a minus b times a plus b. So that's going to factor as 2 minus x times 2 plus x. So I found my common factor. There's a common factor of x minus 2. What do I get when I cancel here? 2 minus x divided by x minus 2. Is that 1? It's negative 1. So that cancels and leaves me a negative 1 behind. And so now I look at the limit as x goes to 2 of negative 1 times 2 plus x. I can put the 2 in there and I get negative 4. What that is telling me is this graph looks exactly like this graph, except at the ordered pair 2, negative 4. There's a hole in it. The ordered pair 2, negative 4 is only something I can get close to but not hit. So it's that same graph, the exact same graph. Go back 2, go up 2, draw you that line. Take the ordered pair 2. Two plus x, that's 2 plus x. Where am I going? This goes to 2. There's no 2 negative 4. Why did I blow a sign? Oh, I should have put a minus sign there. Never mind. So it doesn't have that graph. That's the opposite slope. Let's see. X is 2. That's a negative 4. So it goes here. Here goes down to negative 4. So it goes this way. So when x is 2 and y is 4, there's a hole there. That's the only suspicious point. Everything else is cool. That's called a hole. We'll find the hole with the 0 over 0. In this one, oh, I should have put a negative 4 here. Let's fix our example. Let's make a negative 4 there. This example, I took that same graph, but I plotted the ordered pair 2, negative 4 into it. So this has that exact same graph over there. But this piece comes along and fills it in. G and H are continuous for all values of x. F was not continuous when x is equal to 2. I don't know why I did over here because it's back here. God, I gotta cut back on the vodka. Just go a little bit. That's why you're sitting there looking at me, what? That one has a discontinuity. At x is 2. These are continuous for all x, including x is 2. So a limit is going to have something to do with whether or not a function is continuous at a point. And if a function is going to be continuous at all points, then it's going to be continuous for all values in its domain.
Would that one fill in that?
Yeah, I
the
put it
bottom
back
of the-
down over the bottom.
Okay.
Put it back down over here. This is the upside down day. All right, we'll pick it up from there next time. I'll write the formal definition of a limit, of continuity using a limit. Don't trip on my cord. I'll get it unplugged here real quick.